Hi everyone, welcome to today's colloquium. My name is Peng Zhang and I'm a PhD student of Dr. Han Tangqing's group. He is currently having a Department of Energy meeting, so I take his place. And it is my pleasure and honor to serve as the student host for today's event. And we are very happy to have Shuo Sun here with us. She is a PhD candidate in Industrial Engineering and Operations Research at the University of California, Berkeley. Her research focuses on modeling and algorithm design for supply chain and revenue management using optimization and machine learning. Her work has received several recognitions, including the Inform's Daniel H. Wagner Prize and a finalist distinction in the Inform's IMP Jeff McGill Best Student Paper Award. She has publications in leading conferences and papers published or under revision at leading operations and analytics journals, as well as the industry experience at Amazon and JD.com on retail operations problems. Please join me in welcoming Shuo Sun. Shuo, the room is yours.
Okay, thanks. Thanks, Peng, for the very complete introduction. And let me introduce myself again. I'm Shuo, and now I'm a PhD candidate at UC Berkeley Department of IEOR. And today I'm very excited to share two of my research projects in retail operations, both driven by customer choice behavior. A unifying theme of both projects is how can we develop solution methods that are scalable and implementable in large-scale real-world systems. And I have a page at the beginning for the introduction, but Peng has covered much of it. And I just want to mention, 6 years ago, I did spend one semester here as an exchange student, and this experience really sparked my interest of pursuing academic journey in IE. And so it really feels warm for me to come back. And so I will, yes, and I have some industry experience with JD.com or Amazon on some supply chain operations or platform operations. So now let's go to the party. Is this working? Okay, it's working. So now let's start with something we all experience every day, making choices, whether shopping in physical store or online platforms, or selecting a ride-sharing service or booking trips. Customers are constantly making choices. But if we flip the lens to the side of retailer and platforms, those decisions are always much more complex. They need to decide which product or service to provide. This is assortment, how many units to stock, and how to set the prices. And let me make this concrete using a very simple example. Suppose I walk in a grocery store like the Trader Joe's near this campus, and I was thinking, oh, I want to buy some milk and maybe also grab some coffee or cereal on my way out. But if we consider the problem from the other side, they need to decide which products, which milk SKUs should I carry, and how to allocate the limited shelf space and inventory. Those decisions are very important because if supply and demand do not match, both customers and retailers will pay. Customers cannot get what they want. Retailers will lose sales and the profit, and inventory will be used inefficiently. Over time, this will lower customer satisfaction and retention. So our goal is very clear. We want decision-making tools to help those retailers match supply with choice-driven demand. However, doing so is not easy, and there are several fundamental challenges. In today's talk, I will focus on two of them. The first challenge comes from the demand side. Customer choices are always complex and may span multiple categories. This means we couldn't optimize each category separately and expect to have the right operational decision. But if we consider the categories jointly, how to model it and optimize it for larger space is a challenge. The other challenge comes from the operational side. In real life, inventory is finite, and there could be multiple customers sequentially arriving. So what I put on the shelf in the morning will influence what customers can see in the afternoon. This means there is a trade-off between the profit I can get for now and leaving the room for the profit in the future. Through my experiences in Amazon and JD.com, I've seen these trade-offs repeatedly occurring in retail systems, but of course, it also exists in some platform operations. So my research has been centered around solving those challenges like this, and more specifically, I study how to model customer choice behavior and make more efficient operational decisions. Problem-wise, I study assortment optimization, inventory management, and general sequential decision-making using the methodologies from optimization, machine learning, etc. In today's talk, I will go deep into the two papers that address exactly the two challenges I have discussed. But besides those two papers, I also want to share some other work. I have collaborated with JD.com. This is a major e-commerce company in China on their warehouse assortment and inventory allocation problem in a large-scale fulfillment network using techniques from machine learning, end-to-end learning. And I have also explored robust decision-making in the framework of reinforcement learning. So now let's zoom back in the two challenges we have discussed, and our goal is very clear. How can we build scalable models and algorithms that could support retailer and platforms operations when this challenge of multi-category purchases and dynamic operational environment are present? And of course, even I have claimed retail operations, the methodology actually works for any problems in other fields that share similar structure. Now let's take a look at the previous work. Over the past 2 decades, there has been a rich work in choice-based operations that focus on single category and static settings. By single category, I mean this work assumes customers are only looking at the milk products, but ignore the cross-category interaction. And by static, I mean they typically assume there is one representative customer, so we don't need to worry about inventory. We just need to look at product recommendation. And if we extend from the single category models that focus on only substitutability to the multi-category settings that could have complementarity, or if we move from static setting to dynamic settings, there is also important work, but are much more limited. And the major issue is how can we develop scalable models and algorithms. So in the first part of the talk, I will talk about how we develop a tractable model for the cross-category choice modeling and present a polynomial time for assortment optimization. In the second part, if I have time, I will introduce the advanced algorithmic results for the well-established dynamic assortment optimization and inventory management problem. Now let's go to the first part. And we know that customers often buy multiple products in a single shopping trip, and this figure, it shows the median number of products in a single shopping trip from a large-scale US market study. And more importantly, those purchases are always interdependent across categories. What you buy in one category will heavily influence the preferences in another category. And we can see some examples in e-commerce, grocery, or even travel booking platforms. This motivates a natural but also very central question of how to model the cross-category choices and jointly decide which sets of products to offer. We are thinking about the problem from the perspective of the retailer and platform. We want to help them make decisions about which products and services to offer in each category jointly. So I have said that in the previous work, most work focused on the single category models that only focus on substitutability. Substitutability means adding one product to the assortment will weakly decrease the choice probability of existing products. And discrete choice models are used to model this substitution effect. Mathematically, we use the notation phi I to denote the choice probability of choosing a product I from a set S. And the most well-known choice model is the multinomial logic choice model, ML model. Here, each product has a preference weight Vi, and the choice probability of any product, for example, I, is in proportion to its preference weight. So if we consider a very simple example that a retailer is selling 3 different phones, I, J, K, then the choice probability of choosing I from the set of I and J could be expressed using a very simple formula under the ML choice model. And there are some also very important extensions of ML model that could be suitable for different specific settings. For example, the Markov chain choice model or the ranking-based choice model. I would be more than happy to tell you more about the details of those single category choice models offline, but now let's just keep in mind that ML is a special case of the Markov chain model, and Markov chain model is a special case of ranking-based choice model because we will use it as part of our multi-category choice model later. So given those single category choice models, the assortment optimization problem is to select a subset of products to maximize the total expected revenue. And here, our decision variable is a subset S, and N is a ground set. The expected revenue is given by the summation of the price of each product Ri multiplied by the choice probability. For many single category choice models, the assortment optimization problem is efficient. However, those models ignore the cross-category complementarity. Here, it means purchasing the products in one category will influence the preferences in another. For example, if a customer buys a black iPhone in the first category, she may be more likely buying the black iPhone case in the second category. And in this work, we focus on the asymmetric complementarity. This is usually related to the sequential purchase behavior that the customer first buys some primary products like phones and then buy the secondary products like cases and so on. And this asymmetric complementarity is well documented in empirical and marketing literature. So there has been some important work that consider complementarity. However, they face some common limitations. The most related work proposes a sequential 2-stage ML model where the customer will first choose in the first category, say phones, according to an ML model, and then this choice will induce a separate ML model for the second category. So we can imagine there will be a mixture of choice models for the second category. It sounds like a very natural extension. However, the assortment optimization for this model is intractable at large scale. By intractable, I mean the optimization problem is NP hard, and if we want to solve it exactly, it is equivalent to a mixed integer quadratic program, which we know is in general hard. And in the numerical experiment part, we will also compare the performance of the algorithm for this model. There has been some other related work, but they all face this intractability issue. So besides the intractability, most of those models are limited to the 2 categories, and they are based on the ML model. They use ML to capture the substitution effect within each category. Even we have, say, there is a rich body of work in single category choice models, they haven't been incorporated to the current multi-category model. So our goal is very clear. Can we develop a model that can capture this asymmetric complementarity, is computationally efficient for assortment optimization, and is also more flexible to handle more than 2 categories and go beyond the ML choice model? And this is exactly the contribution of this work. Here, we propose a new Markovian model to capture the cross-category complementarity, which is tractable for both estimation and optimization at large scale. So let me first give you some high-level idea of the difference from previous model. Here, we assume the choice in the first category, let's say I, it will decide the initial arrival distribution over products in the second category, those lambda values. And once we know which product this customer is initially interested in the second category, they can still substitute to other products, but the substitution part follows a fixed choice model for B. So in this model, we are only mixturing the lambda values, not the choice model for B completely. And this structure, it buys us a lot. For modeling, we can allow a large class of models for substitution within each category, and we can model any directed acyclic graph structure. So this figure is an example of 4 categories, A, B, C, D. And for optimization, we have a polynomial time exact algorithm for a larger class of models for substitution within each category. For estimation, we develop an expectation maximization algorithm to learn the model from data. And I will also show you the experiment results to show the model improved prediction accuracy and assortment decisions. Now let's start with the model, and I will walk you through the model with 2 categories and then extend to multiple categories. Now let's say there are 2 categories A and B, and we have a choice model phi A and phi B to capture the substitution effect within A and B respectively. Here, phi A and phi B can be any ranking-based choice model. It includes Markov chain model and ML model as special cases. And then the customer comes, and she will first look at the first category, category A, and follow the choice model phi A. Let's say this customer chooses J, and what will happen next? With probability lambda jk, she will be initially interested in product K in category B, and with this lambda jk value indicates the strength of complementarity between product J and K. If lambda jk is high, this means there is a stronger complementarity between product J and K. Then let's say with probability lambda jk, the customer initially considers K. What will happen next? If K is offered in the assortment as B for category B, the customer will buy it directly. Otherwise, the customer will substitute to the other available products according to the fixed choice model phi B. So here we can see the choice in category A, it only influences those lambda values, initial arrival distribution over products in B. But once we know the starting point in category B, the substitution process, it follows a fixed model phi B and is independent of the choice J in category A. We call it Markovian structure, and as we will see, it is really important for the optimization algorithm. And I also want to give you a special case to illustrate what I mean by the substitution process. Let's say this phi B is a simple ML model. Then recall that in an ML model, each product has a preference weight V. So here, if the customer initially arrives at K in category B and K is not available, this customer will transit to product L with probability VL divided by VL plus 1. This is the standard formula for a single category choice model. And we call it Markov ML, and I give it a name because we will use it in the experiment. I also want to say using the having the Markovian structure doesn't mean we ignore the influence of the category or the choice in the first category on the substitution process in category B. Let's think about a very simple example that a customer chooses black iPhone in category A, and it is very likely that she will first arrive at black iPhone case in the second category. So if black iPhone case is not available, oh, this is a mental model. I don't mean the customer arrived at some product that is not physically present in, say, Apple Store. It is a mental model that the customer's initial interest is this black iPhone case. Then if black iPhone case is not available, due to our Markovian assumption, we say this customer will transit to all the other products in the same way as all the customers who also start with the black iPhone case. So if the choice model phi b is rich or expressive enough, it should be able to capture the effect that if starting from black iPhone case, customers will be more likely to transit to iPhone cases of a similar color, but it's not possible to transit to other cases like Samsung or Google cases. So I want to say the choice of this black iPhone, it still influences the substitution process in the category of cases by changing the starting point of customers' selection process. And this two-category model, it can be extended to any general directed acyclic graph structure. Here, each node is a product category, and an edge from like A to B means customers often move from A to B. It can model some different structures like a chain structure, a convergence structure, or a tree structure. Yeah, now we have the model. I'm going to talk about the optimization. Here I will focus on the polynomial time for unconstrained optimization, and would be happy to talk about the cardinality constraint setting if I have time or offline. And the assortment optimization problem is to jointly select a subset from ground set of A and a subset from B to maximize the total expected revenue. Here, we focus on the case that both assortments will be displayed together to the customer. Even our model can also handle the sequential recommendation setting. That is easier for recommendation. So now, if we write it in the formulas, it is a summation of the prices of any two options multiplied by the joint purchase probability. Here I use the P term to denote the joint purchase probability. It will include the phi A, phi B, and the lambda values. I use P here to give you a high-level idea of the problem, but I will be happy to talk about the detailed formula offline if you are interested. This two-category assortment optimization problem is very challenging in general. The first challenge is that now we are thinking about the joint decision of two categories. Solving it is close or is equivalent to a mixed integer quadratic program, so it is in general very hard. And another thing is, for the previous mixture model for category B, even when we know the optimal assortment for category A, solving the optimal assortment for B is intractable if we have a mixture of choice model for phi B. But now, the good thing is we are only mixture those lambda values, and the substitution follow a fixed model phi B. So we can actually have a very good property that there exists an optimal assortment in category B that is independent of those initial arrival probabilities, those lambda values, and it can be computed in polynomial time. This means for this two-category problem, we can actually effectively decouple it and starting from the second category and first calculate on the invariant optimal assortment for it. And then we go back to the first category. Here, we will calculate an adjusted price for each product. For example, the adjusted price of product I includes its original price plus the expected revenue from category B, conditioning on purchasing A in category, I in category, J in category A. And this part, it incorporates the complementarity between product J and the assortment ISB in category B. So this is for two category, and then I will show it can be extended to any directed acyclic graph structure. Here we will first sort all the product categories in the reverse topological order and compute the optimal assortment for C and D, and get SC star and SD star, and then go to category B and calculate its optimal assortment, and then go to category A. So this is about optimization, and I want to pause here and see if you have any questions for either the model or optimization. Yes, please.
Is this framework correlated with dynamic programming? And I noticed that dynamic programming can also be generalized to DAG and something like this.
Yes, yes.
From the back to the first.
Yes, that's a great question. Yes. So essentially, the DAG algorithm, it is a simple version of dynamic programming. It is backward induction. And the key of why it works is we can prove the invariance of some optimal assortment from the end. So we can go from the end and then go to the starting point, starting category. Oh, that's a very good question. So here, we actually assume this happens in one transaction. So the customers first make a selection in A and then B, and then go to C and D. Yes.
And then the split off, is there a specific reason for that? And I might have missed that. Is there a specific reason you're splitting off B and C two nodes rather than just sequentially?
Yes.
I want to solve 10 stages or something like that.
Oh, yeah, thanks for the question. This split is because sometimes, let's say, for example, the customer buys a phone. She may be interested in both the phone cases and the screen protectors. But cases, they have substitutability within the case category, and screen protect has its own category. So the customer can choose in both categories. And both of these decisions are dependent on the category of phones.
Okay. One follow-up question. In practice, how you decide the order of A, B, C, D? Like what product is A, what product is B?
Yes.
Yeah. How in practice, how can we get this information? Because in one transaction, we just get one receipt.
Yes.
We really don't know the order of the product the customer picks.
That's a really good question. So if we have like the timing of the purchase, like in the e-commerce data, it will be easier to get it. But I agree that in some grocery or physical store setting, we only have the receipt. So here, let's think it in different scenarios. If we only have two categories, we always have some domain knowledge, like customers will first buy the phones and then buy the cases, and there is some literature from marketing or empirical economics that says the asymmetric complementarity, that we could borrow the knowledge from the literature and some domain knowledge. If we have more categories, we can, in principle, using expectation maximization algorithm to estimate the edge, the weight of each edge in this DAG, and see if it has a dominant weight in this direction over other direction. But that needs much more data. So I agree that for a big graph, that's a challenging problem.
So the proof for the independence of the category B choices, can you give us a hint about what is the primary method that achieves that? Is it the Markovian assumption, or is something else going on? Can you give us some?
Yeah, sure. Yes, let me give you two.
I think you had the previous slide.
Yes. And
yeah, so.
Actually, I have. It's here. Let me skip to this. Yes, I have an explanation here. Okay. So actually, for this, the key is we are mixturing the lambda values. So given any optimal assortment for SA, we actually have a set of lambda values And then we look at category B. It becomes a single category choice model. So here, let's say, yeah, it's a single category choice model. And if when phi B is a Markov chain choice model itself, the optimal assortment is invariant to those lambda values, because the high-level idea is to add the products that has a high modified or adjusted price, and in that formulation of the adjusted price, it actually only considers its own price minus the expected revenue it blocks from other products. But both parts are independent of those lambda values.
I have kind of related questions.
Mm-hmm.
So what happens if the structure is like a downside triangle, like a child to two parents? In this case, when you first solve the child, will the theorem still hold? Or when you're solving the parents?
How two parents or two children?
Two parents. Like A, B is the first category, B to C.
Yeah.
Once you solve C, will the A, B solution be unique or still
It still works for that setting. So if there are two parents and one children, we can still start from the children and then go back to the parents.
So the solution for parents still unique in this case?
Unique, you mean?
Can you still find the unique solution?
For the
parents?
Yes. 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 Yeah, thanks for those questions. Now let's go back to, is it working? Oh, it's going to the teaching plan. That's hard. Sorry, there is something messy when I create the super links. So now let's talk about the estimation. And here, let's first see what we can observe from data. From the training data, we can see the assortments and customers' choices. And our goal is to infer the choice model and the transition matrix. So the main challenge here is that now the log likelihood function is not jointly concave in those problem parameters. And what we do is we define a set of latent variables. For example, xk is a binary variable indicating whether the customer is initially interested in k. And the good thing is, with this latent variable, the log likelihood function will be jointly concave in the model parameters. Then this leads naturally to the expectation maximization algorithm. In the E step, we will evaluate or calculate the conditional expectation of the latent variables. And then in the maximization step, we maximize the log likelihood function. Because it's not jointly concave, we can solve it using a standard solver. So now let's talk about experiments. So far, I have shown the model is tractable for both estimation and optimization, but you may also wonder, some independent models can do all of this, so we really need to show that it is important to incorporate complementarity from data, and our model is really doing much better than the independent choice models. So here we have results for both synthetic data and real-world data. Let me start with the data sets. For the synthetic data, we generate the transactions using a very general ranking-based choice model. And here, we control the strengths between complementarity using the parameter theta, so we can see its influence on model performance. For the real-world data set, we use a large grocery data set from a major US retailer that includes near 6 million purchases over 90 weeks. For comparison, we compare our model that uses ML for both phi A and phi B against the two ML-based benchmarks. This multi-ML is the closest one to ours. It has a mixture models for B, and independent ML is simply two independent ML choice models. Yeah, let me briefly introduce the results for the synthetic experiments. This page is the result for log likelihood value and hit rates. Hit rates is a metric for prediction accuracy, and blue line is the performance of our model. Green line is our model. Blue line is for another model, and red line is independent model. We can see For both model fit and prediction accuracy, our model and the multi-ML model are much better than the independent choice models, and this benefit increases when the strength of complementarity increases. And also, for the synthetic data, we also compare the decision quality in terms of the expected revenue under the ground truth model. So it is interesting to see that even multi-ML, our benchmark with complementarity, and independent ML have different performance for model fit and prediction accuracy. They often output the similar assortment decisions, and our model output a different assortment decision and achieves higher expected revenue under the ground truth. I also want to provide a quick comparison of the running time because I have claimed we have a polynomial time algorithm. So here I implemented our algorithm using Python and implemented the mixed integer quadratic program of the benchmark model and solve it using Groovy, also coded by Python. And here we can see for both unconstrained optimization and constrained optimization, the running time of the benchmark algorithm increases almost exponentially in the number of products, but our model is very stable. If we put them on the same scale, it is near constant. And for the cardinality setting, the benchmark model cannot solve it even for 60 products, but we can scale really well. Next, let's talk about the real-world experiments. Here, for real-world data, we don't have a parameters data to control the complementarity strengths. So our first step is to identify the categories that do have strong complementarity and distinguish it from the so simple co-occurrence setting like the classic diaper and beer case. So here we define a heuristic metric, and I will skip this metric and due to the time reason, but I will be more than happy talking about it offline. Essentially, we are comparing the difference between the marginal choice probability for B and the conditional choice probability for B. We also validate this metric on both synthetic data and real-world data. So finally, with this metric, we identify some categories that do have strong complementarity. Here I will show you the case study of cake mixes and cake frosting. These are two categories. And this table shows the log likelihood function, LL, and hit rates, ranking accuracy for different models. The third column and fourth column, hit rate and rank accuracy, are both metrics for prediction accuracy. So here we can see both multi-ML and Markov ML, our model, they are much better than the independent ML model in terms of all metrics. And you may also observe that it seems our model and Markov ML and the multi-ML have similar performance. And I want to clarify again that our model has a clear advantage of tractability for assortment optimization, while the assortment optimization is intractable for the multi-ML model. Finally, I also want to show the model itself is not a black box. It can actually discover some interesting managerial insights here by leveraging the estimated model parameters. We find a strong brand matching effect that a customer who buys a cake mix of a particular brand will be more likely to buy the cake frosting of the same brand. So that's the first project here. I want to conclude by saying here we propose a new Markovian model to address the problem of cross-category modeling and assortment optimization, and it is tractable for both estimation and optimization, and estimation and optimization, and we also did experiments from both synthetic data and real data. And this is the first project. Let's go back to this map. However, in this work, we still say there is a representative customer, so we only need to recommend products to them. There is no inventory. But I have to say how to make the decisions in the dynamic environment is a challenging problem. Here, inventory is finite, and products could be out of stock. So now I will talk about my second project. And don't worry, I will focus on the main methodology and the main results. So here, let's still first look at the problem. Here we consider the dynamic assortment problem, optimization problem, that there are multiple customers, and we use T to denote the number of customers. Here, each customer has a random preference, and in this setting, inventory rarely matters because assortment will change as inventory depletes over time, and we can see it in both physical store and e-commerce platform. And let's see the formulation or the demand process of this problem. Let's say we start from 2 units of gray product and 1 unit of red product, and the customer makes a choice according to ML choice model, the most classic choice model. And this first customer, she has 3 options: choose gray, red, or choose nothing. And if gray is not, the customer chooses gray, then we can see for the second customer, she can still see both red and gray in stock. But if the first customer chooses red, then red will be out of stock. So the second customer can only see gray, and the choice probability of gray will also change. So this coupling between stockouts and stochastic customer choices are the essential challenge of this optimization problem. Stockouts will influence customers' choices. Also, customer choices will influence the sequence of stockouts. And here, I also want to bring the optimization problem here. We are interested in finding the starting inventory to maximize the total expected revenue under some constraints. And here, C is the starting inventory vector, and T is the number of products. FCT is the total expected revenue. And more specifically, here we consider 2 different constraints: cardinality constraint and knapsack constraint. Due to the time, I will skip this part. Here we also consider a personalization setting that the retailer can choose to only show a subset of products, like the e-commerce setting. And the problem, it is known to be very challenging because first, we don't know the number of customers, and even evaluating the objective function is a very open problem. For ML, current methods rely on Monte Carlo simulation, and there is no known good structure for optimization. The objective function is neither monotone nor submodular. And I should also emphasize that our inventory vector C is an integer vector. So this is an integer, it's like an integer programming problem. And moreover, there is even no good relaxation for the no personalization setting where the customers can see all the available products. And our goal is to develop a constant factor approximation algorithm that achieves at least the alpha factor of the optimal objective function. And here, this page, it summarizes the state-of-the-art results in the previous work. I want to emphasize that for the no personalization setting, like the grocery store setting, the previous methods, it rely on using simulation or Monte Carlo simulation to estimate total expected revenue, and then use enumeration to identify the size with the highest expected revenue. So we can see there are 1 over epsilon in the running time, and both of them are limited to the cardinality constraints. And also there is some limitation in the personalization setting. And our contribution of this work is to propose a unified algorithmic framework for both settings that achieve state-of-the-art in both runtime and performance guarantees. Here, I will focus on the no personalization setting, and we can see that it improves the running time a lot because now we don't rely on simulation or enumeration. We actually identify a good relaxation for the original stochastic problem, and our algorithm is based on the relaxation. So in the algorithm, first, our algorithm has 2 steps. First, we optimize fluid relaxation. Here, it is based on the linear program. And from this part, we can get a feasible inventory C1. And then for the no personalization setting, we transform it to a feasible solution to the original model, original problem, and we call it C-alg. And for the personalization problem, we have similar online assortment policy for different settings. And the analysis framework also has 2 steps. In the first step, we will get an alpha approximate, and in the second step, we will relate this relaxation to the original stochastic problem and have a beta approximation factor. Combining both alpha and beta together, we will have the final performance guarantee. Let me focus again on this no personalization setting and show how we get those alpha and beta values. It is here, alpha and beta. So to analyze it, let's first look at the relaxation. Here, we use a linear program-based relaxation. We have a decision variable ys to denote the probability of choosing a subset S to offer to customer, and the objective function is the expected revenue for T customers. We have an inventory constraint that limits, or this requires, the total consumption of any product I is upper bounded by its starting inventory Ci. We have a normalization constraint. And this linear program, it actually relaxes the original problem in 2 ways. First, it is a deterministic fluid relaxation. So now we don't say a customer will purchase a product according to an ML model, say by product I with probability 0.5. We say this customer buys 0.5 unit of the products. So it becomes from stochastic go to deterministic, and it allows for personalization. So we have this decision variable ys, so it can offer a subset of products. It is not like in the no personalization setting, we say in a grocery store, we just set the starting inventory and customer can see all the available products on the shelf. So even with this fluid relaxation, how to maximize the C vector under some constraint. Here the C is the right-hand side in this LP. This is still a hard problem because C is an integer vector. So we explore and prove this objective function have a sum modular order property. It is a relaxation of the sum modularity. It's a diminishing return property if we put the items in a specific order. With this diminishing return property, the threshold-based approximation algorithm can give us a half approximate. So this is a half we have, and then let's see how we get the beta value. And this part, it is the harder and it's the main challenge for this no personalization setting. Because we have say, this LP, it relaxes the original problem in 2 ways. So to bound the gap between this LP to the original stochastic problem, we really need to bound the gap that comes from those 2 relaxations. So we need to get gap from fluid and to stochastic and from personalization to non-personalization. And in fact, for general choice models, I have counterexamples showing this gap could be arbitrarily large. But for ML, we can actually show the stochastic gap is 1 minus 1 over E. This matches the stochastic gap for many classic online matching settings, but here the analysis is very different. And the personalization gap is 1 minus 1 over T. So this is the beta factor we have for the second step. If we combine this beta factor with the 1/2 for alpha in the first step, we will get the final approximation guarantee. And that's the second product. Here, we focus on how to develop a 2-step algorithmic framework for faster and also more effective decision-making. And I want to conclude here that a unifying theme or goal of both projects is to develop scalable models and algorithms for some fundamental problems in choice operations when we move toward richer customer preferences and dynamic decision-making. So now I will talk about my future research agenda. I will be interested in efficient modeling and algorithm design for key operations in supply chain management. The first topic I'm interested in is the choice-based operations in the age of generative AI. So now we, as customers, we actively interacting with ChatGPT or specific shopping assistants like Amazon roofers. We are not just browsing the products as I assume in the two projects. So in this topic, I want to study how this AI's recommendation or interaction will change customers' preferences, and do we need to develop new operational model or optimization model to adapt to the trend. And I plan to approach this topic in multiple steps. We first need to understand AI's preferences. Does it have substitutability or complementarity? And with this understanding, do we need to develop new optimization model, or can we better align humans' interest with some AI agents' recommendation? So for this topic, I can see many potential interdisciplinary collaboration opportunities. I also have ongoing work in this topic that studies the influence of LLM on customers' attitude or preference to pricing. In the second topic, I'm interested in the algorithmic decision-making for the fundamental problems in supply chain management and revenue management. There have been some natural extensions of these two work, like go beyond ML and go beyond substitutability, but I'm also very willing to explore the applications in different industries, not just the retail and fulfillment networks, maybe also explore choices in manufacturing or even healthcare, and I'm willing to explore more data-driven or machine learning-based methodologies. And I want to end here with my teaching plan. This big table, I list the courses I will be very happy to teach or co-teach at Madison SYE, because I have some teaching experiences at Berkeley for different levels of supply chain optimization and analytics courses. So I will be more than happy if I have opportunity to teach those supply chain optimization or machine learning courses or co-teach those courses. And if I have opportunity, I also want to introduce algorithmic decision-making for supply chain that could be tailored to different levels of students, and also include some applications of generative AI for industrial engineering students. And I will end it here, and I'll be happy to take any questions you may have.
You mentioned about extensions to manufacturing and other industries.
Yes.
So the work that you have done so far has been in the context of business to consumer.
Yes.
So help us understand how this work can be extended in the business-to-business domain, like in manufacturing or similar sectors.
Yes, that's that's a very good question. I think for B2C and B2B, there are some differences also, but some also connections. So now I'm saying the demand are driven by choices, and I'm thinking maybe in B2B business, some demand may also be driven by the choices of the manufacturing or some companies' requirements. So if we have those choice-based, so if we have these choice models, then these methodologies will be applied naturally to the context. But for those applications, I want to say that my work has been focusing on scalable optimization and these things. If I want to study manufacturing, I still want to first start from the real needs of the problem, the limitation, and then see if those methodology can be applied to those problems. Thank you. Yes.
Microphone, because I think it is videotaped, so we want others here. So my question is about that real-world data study. Can you give a little more information? I have two questions about that. First is, you said it's like 5.68 million transactions.
Oh,
right?
yes, yes.
Is this like a public data set? You don't have to give the name of the company, but is it private, public? Did you have interactions with the company directly? Can you give a little more information
The
on
real
that?
data it comes from a joint project between Stanford and Berkeley for retail, so people can get access, apply for access for that data. And I found that data from some previous paper, and it comes from a store that everyone know here, but I will keep the name. Yes.
But you do not interact with the actual sort of. That's it's uploaded data. You just analyze the data and run your algorithms, right?
Yes, exactly.
So I don't know if you had ever compared. I understand the computational performance is great, but did you ever compare your method to the other methods in terms of, are there any concrete differences between the suggested assortment between your method versus others? Like, I don't know, maybe you put more black iPhone cases in the next to each other, or I mean, is there any way where the algorithm not just overall performance differences, but really lead to the design of the assortment planning? And did you have any observations? And if so, can you share with us?
Yeah, that's a really good suggestion, actually. So currently, I only evaluate the performance of those assortments on synthetic data. But I think it's very interesting to see maybe some qualitative difference of the recommended assortment decisions from real data.
Okay, so you didn't do that, but
I think that's
is that possible? Can you do that in the data?
Yes, of course. For the real data, we run the estimation of the model, and then we calculate optimal assortment. So it is easy to compare the difference. But compare the expected revenue is not doable, because for real data, we don't know the ground truth model, but we can still do some comparison and see some insights from it.
Okay,
thank you.
I have one question. Yeah. Did you do the sensitivity study for your first work? Like, you estimated the Markov model may have some uncertainty. So how that will influence your final solution?
Oh, that's a
sensitivity study typically.
Yeah, that's a great suggestion again. So currently, I don't have sensitive analysis in the paper, and it would be helpful to add a robustness check. But I actually also want to say, for those discrete decisions, there should be some robustness against the change of model parameters. But that's a very good suggestion, and I will explore it in the future.
Hopefully this is not really out of scope, but what's the span of the data collection from the data? Because my next question is, in general, how do you treat new products? And usually products have this product life cycle issues, and then over a year or so, there's probably new products coming. Like, how do you treat those in these models or in this analysis? I hope that makes sense.
Yeah, that makes sense. And thanks for your questions. And I want to make sure I understand the question. The first is about the spend of data collection process, right? So this data set, it comes from the scanner data at a grocery store. So I'm not sure about the exact how much they spend, but I think it is doable. They keep the receipts. They have some machine recording it. And your next question is about launching new product. And that's a very important question in these related problems. People can see if there are any similar products and similar, or calculate the combination of features to see if what's the similarity, and if there is a similar product, what was in the historical data. And another thing people do is if we have a featurized model, that would be very helpful, because when a new product comes, it also comes from different features. So we will be easy to see its customers' preferences. Another thing is people also use some online learning methods or even large language model to get a sense of how the product will it be popular in the future, and should we launch it or not in a process. Yes. Oh, and also you also ask about the life cycle. Oh,
in general, like, when you have a new product, there's products going in and going out. Like, how do you consider that in the model? Like, some products become obsolete, and then, first you already address the new products, and then how about like those that are obsolete as well? I don't know if that's like
yeah, that's a very good point. Currently, the model there is no the consideration of the life cycle. But I think when we talk about the inventory, the life cycle is a very important problem because some fresh products, they will be abandoned maybe at the end of the day. So that's a very good point, yes.
Yeah, okay. Thanks for Shuo's excellent talk, and this concludes this colloquium. And besides this colloquium, Shuo will have a meeting with PhD students at ME 3210 at 2:30 p.m. and this welcomes every PhD student to join. And yeah, thanks again for everyone to join. Thank you.
Thank you.